Right, let's have a look at this question then. Right. Hoops in a magnetic field. Explain why an EMF is induced in the hoop as it expands. Key bits, the area inside the hoop changes. So the flux linkage changes. There's therefore going to be an EMF induced due to Faraday's law. 3 marks. Area changes, 1 mark. So the flux linkage changes, 2 marks. When the flux linkage changes, there's an EMF induced according to Faraday's law. Explain why the current flows anticlockwise in the diagram. Well, like what I mentioned on the previous question, Fleming's left-hand rule. Use that. And there should be a force inwards. This is expanding outwards. Lenz's law said there should be some opposition to that. There must therefore be a force acting inwards. If we use Fleming's left-hand rule, the field is into the page. If I get the current flowing that way round, my thumb is pointing towards the centre. The force should be to the centre at all points. It's quite awkward because I've got my camera balancing on some old offcuts of wood, so I can do this. There's another way of explaining this as well. If you have indeed got your current flowing round that way, you've got a current in a wire. Therefore, a magnetic field is produced. Use the right-hand grip rule. Current up on the right-hand side, the field would be coming out the page in the centre of the coil. On the left-hand side, current down, field coming out of the page in the centre. The fact that there's a field produced out of the page acts to reduce the overall magnetic field. The magnetic field we've got here is into the page. We're producing one out of the page. It acts to reduce the resultant magnetic field and hence is opposing the change that is causing the induced EMF. Anyway, I think that's an easier explanation. Right, next bit. Okay, you've got a radius here so you can work out the final area of this. Induced EMF, rate of change of flux linkage. There's one term, there's one magic wand. What's that number? That is the flux density times by the area. NBA. Again, I don't need to worry about the cos theta in this one. Change in time, 63 milliseconds. Bang that lot in, 0.278 volts. The EMF over the resistance would tell you the current, 0.63 amps. Bish bash bosh. This one. Why is there an alternating EMF induced in the coil? The flux is changing and hence an EMF is induced. However, that flux is alternating as the magnet changes direction. The south pole gets closer, the flux is increasing. The south pole moves away, the flux is decreasing. So you've got some positive and negative rates of change of flux there. So you have positive and negative EMFs. Right, I've skipped this bit out. You don't actually need to be able to do this. RMS values. We don't need to worry about AC theory for our course, but if you are interested in this, you can take your peak value of voltage and divide by √2 and you'll get the mean magnitude of your voltage. Look it up if you're interested in that. I'm not going to even bother writing the answer to that bit. State the value of the rate of change of flux linkage through each turn of the coil when the peak value of 0.707 volts is obtained, and explain how you obtained your answer. The induced EMF, I suppose I'll put a negative in. Rate of change of flux linkage. If I divide through by the number of turns, because we want the flux to each turn, that is the rate of change of flux per turn. I've divided through by n. There are 200 turns. Divide your peak voltage by 200, and that is the rate of change of flux linkage through each turn. Done. One end of the coil is connected with the other, so there is now an induced current. You can't get the current without a complete circuit. Explain why the magnet's motion is now damped. When a current can flow, a magnetic field is set up that opposes the motion of the magnet due to Lenz's law. Energy will therefore be dissipated in the form of heat in the wires when the current can flow. So as this south pole moves towards this coil, this acts like a solenoid. There's an induced EMF, there's an induced current. The current will flow around such that there is a south pole at the top to try and repel that away. As the south pole moves away, the EMF changes direction. The current will flow in the other direction, so that there's a north pole here trying to pull the south back down. It's always going to be acting to oppose the motion of this. Because there's a current induced, there's going to be heat dissipated in the coil. It's going to be transferring the kinetic energy of the magnet into heat dissipated from the coil. That's what's going on there. Now, I think that's the last one I'm particularly going to go through with you guys. I'd recommend you do indeed finish all of those questions, and you can check the answers out on Moodle if you need to. Any questions, just ask.